All right, yeah, so this is unique games hardness of quantum max cut and a conjectured vector value Borell's inequality. This is joint work with Yangwu Huang, Ojis Parek, who's sitting in the second row there. Hi, Ojis. Kevin Thompson, and then Joe Neiman. All right, so before I tell you about quantum max cut, let me tell you about the classical problem of classical max cut. So in the problem of classical max cut, you're given a graph G equals V comma E. And what you want to do is find a cut of the graph. So you want to partition the vertices of the graph into two sets so as to maximize, so in this case, maybe we have one set is a blue set, the other one is the orange set. And what we want to do is count the number of edges that cross the cut, that go from a blue vertex to an orange vertex. This cut, it cuts 7 of the edges in the graph. But it turns out you can do better than that. So if we set this to be the blue vertices and these to be the orange vertices, then you can look and count. These are the edges in red that get cut by this cut. And if you count, what you find is that this cut cuts 8 of the edges. And this is actually the maximum cut in the graph. So in general, our goal is to find our partition F, which maps the vertices into the blue set and the orange set, which maximizes the following quantity: the sum over all edges U comma V of the indicator that the color assigned to U, F of U, is different than the color assigned to V, F of V. Okay. And one thing that we'll do throughout this talk, rather than assigning it to the blue and the orange set, is we're going to rename the blue set the +1 set and the orange set the -1 set. So in the picture, all of these become +1 vertices, and then all of these become -1 vertices. And then if you do that, the indicator that F of U is different than F of V can just be written as 1 minus F of U times F of V over 2. So if F of U and F of V are both assigned +1 or -1, this is 1 minus 1 over 2, which is 0. And if they're both assigned different numbers, then what you wind up with is 1 minus -1 over 2, which is a 1. So this is indeed 1 if F of U is not equal to F of V, and it is 0 otherwise. So this problem, it's like a classic problem in computer science. It was shown by Karp in the 60s, I think, or maybe 70s, that this was NP to solve exactly. And so what people in theoretical computer science do is instead they look for approximation algorithms, which try to find the best possible solution. And so the definition that we're going to be using throughout this talk, an algorithm achieves an alpha approximation if it outputs a partition F such that the number of edges that F cuts is at least alpha times the maximum cut in the graph G. So alpha here, it's always going to be a number between 0 and 1. You can never do better than the maximum cut, so you can't have alpha be bigger than 1. And in general, what you're trying to do is get an algorithm that gets as big of a value of alpha as possible. Okay, so what do we know about approximating max cut? Well, there's a famous algorithm due to Gomez and Williamson from 1994. It runs in polynomial time, and it achieves an approximation ratio of 0.878. So whatever the maximum cut in the graph is, it outputs a cut that is at least 0.878 times the value of that cut. Their algorithm, it's based on this powerful and general technique known as semi-definite programming, or SDPs. I'll talk more about what this is later. And like I said, this is a powerful and versatile framework for designing algorithms, not just for max cut, but for a large variety of optimization problems. Follow-up work by Koch, Kindler, Mossel, and O'Donnell, and then Mossel, Oleshkovitz, and O'Donnell showed that this Gomez-Williamson algorithm is actually the optimal polynomial time approximation algorithm for max cut. So actually, any polynomial time approximation algorithm will get an approximation ratio which is 0.878 or worse. Except one caveat, they assumed something called the unique games conjecture, or the UGC. If you're not familiar with the UGC, it's just one of the big unsolved problems in the field of approximation algorithms. It used to be like a very controversial conjecture. About half people believed it's true, half people believe it's false. But now I think most people are on the side of it's probably true. So if you assume this, definitely true conjecture, then indeed Gomez-Williamson is the best thing. Okay, so max-cut is an example of a specific example of a more general class of problems known as constraint satisfaction problems, or CSPs. A CSP in general, it's just a set of variables with constraints on them. So like in max-cut, your variables are each of your vertices, and the constraints are that neighboring vertices should get different values. And there are many, many examples of constraint satisfaction problems in CS. So for example, max 3 set, max 3 coloring, max 3 XOR, these are all classic examples of constraint satisfaction problems. Now you might ask, how do you approximate these constraint satisfaction problems? Well, it turns out that for every constraint satisfaction problem, there is a semi-definite programming algorithm that you can run for it. There's kind of a canonical one that everyone likes to use. Sometimes this is also called the basic semi-definite program. And what Raghavendra showed, so this is like following up on the work of Mussel, Oleshkovich, and O'Donnell and KKMO, he showed that the basic STP is always the optimal polynomial time algorithm for every constraint satisfaction problem, again, assuming the unique games conjecture. So this gives us a complete understanding, not just of the approximability of max cut, but of the approximability of all constraint satisfaction problems, at least modulo the still unproven UGC. And this just gives, in addition to giving us a complete and total understanding, it's a beautiful theory. It's like one of my favorite theories in all of computer science. There's so many amazing results that have come out of it that not only touch on approximation algorithms, but touch on other areas of mathematics as well. Okay, but this talk is not about classical CSPs. It's about this quantum problem of the local Hamiltonian problem. So I'm sure everyone here knows what this is, or probably many of you do, but let me just say it's kind of like a quantum version of constraint satisfaction problems. So your input in general with a local Hamiltonian problem, it's a physical system that looks like this maybe. Yeah, so it's like some particles and some constraints between the particles. And your output is going to be either the ground state of the system or maybe the ground state energy of the system. Okay. So these yellow dots, they're like your qubits. These are like the quantum analogs of variables. And these red lines are your quantum constraints. So this is indeed like a quantum analog of constraint satisfaction problems. And not only is this like a basic problem in computer science, it's also a very important problem in physics. So people have studied local Hamiltonians for, about 100 years, maybe more. Okay, so what is the actual input? So the way we specify a local Hamiltonian, we're going to have a graph G on n vertices. So pictorially, this graph will specify the n vertices of this graph will correspond to 1 qubit apiece. And so if we have an edge U, so every vertex in this graph is going to be associated with some vertex, so one of the qubits. So maybe this qubit here is like the U vertex. And then in addition to this graph, we're also going to be given a Hamiltonian H. And the Hamiltonian H is going to be the sum over every edge in the graph of HUV, which is going to be like a local term on qubits U and V. So if U is this qubit here and V is this qubit over here, then HUV is just going to be a local term that acts on both of them. So it's going to be, if they're qubits, this is going to be a 4x4 matrix. And we're always going to implicitly assume that there's like a tensor identity here. And that allows us to extend this local term, which acts on 2 qubits, to a term that acts on all n qubits. But typically, we won't write that tensor identity. It's just always assumed. Now, our output was going to be the ground state or the ground state energy. So what does that mean? Well, that means that we want to output a quantum state psi on n qubits that has a minimum energy on this Hamiltonian H as possible, where the energy is defined as psi h psi. Now, actually, in this talk, we're going to do like a little bit of a switcheroo, which you may not have seen if you work with local Hamiltonian problems. So we're going to, instead of working with the minimum energy, we're going to be looking at the state with the maximum energy. This is like equivalent. If you want to look at the Hamiltonian H and look at its minimum energy, it's equivalent to looking at the Hamiltonian minus H and looking for the maximum energy. And the reason we do this is that it just is easier to talk about approximation algorithms when we have maximization problems. So we're just going to be looking at the maximum energy state. And the energy of the state, well, it's the maximum overall psi of psi h psi. That's just the maximum eigenvalue of h. Okay, so that's our goal. You're given this h, find lambda max of h, or find this psi, which maximizes it. Now, there are some problems with this local Hamiltonian problem. Is that it's a much less understood problem than classical constraint satisfaction problems. So it turns out there's a lot to do in this area. So for example, what we do not have is a theory of optimal algorithms. So, in classical CSPs, we had the Raga-Vendor result that always told us what the best algorithm was for the local for CSPs. We don't have that for the local Hamiltonian problem. We also don't have a good understanding of the power of semi-definite programs. I mean, you can write down semi-definite programs to help you approximate local Hamiltonians. We just don't know how good they do. What we do have are different types of semi-definite programs. So we have level 1 semi-definite programs, level 1.5 semi-definite programs, level 2 semi-definite programs, and so on. Each one of these has a different amount of power in approximating the SDPs, but we really don't know in general how well do these different SDPs perform. And we don't know whether any of these are optimal. We don't know if any of these kind of correspond to optimality in the same way that the basic SDP did in the classical CSP world. We also don't have a quantum version of this thing called the PCP theorem. So I know Chinmay, I think, talked about this. Either he's talking about it or he already has talked about it in IPAM. But the classical PCP theorem is like a very important result in the approximability of CSPs. But we don't have the quantum analog of that statement. So there is a quantum PCP conjecture, but it remains a conjecture, so it's still unproven. All right, turns out there's another problem with the local Hamiltonian problem that's like unique to it and which doesn't occur at all in the classical world, which is known as the ansatz. So for your local Hamiltonian algorithm, what you're supposed to do is output a quantum state psi with a large energy. Well, what does it mean to output a quantum state psi? Well, if you're designing a classical algorithm, to output a quantum state, what it really means is you should output a classical description of psi. And for my polynomial time algorithm to be able to output a classical description of psi, it must be the case that psi is efficiently describable. So it must be that I can describe the state to you using only polynomial bits. So for example, a general quantum state requires exponentially many bits, but we do know that there are nice classes of states that can be described efficiently. So for an example is a product state, where psi is just, it's a separate pure state on each qubit, and the whole state is a tensor product of all of them together. This thing, you can describe it just by describing each of the individual qubits. And since there are n qubits, this requires about order n bits to describe. So this is an efficiently describable state. Okay, so you can talk about this more generally and call an ansatz just to be a family of quantum states which is efficiently describable, which we would like our algorithm to output. But this motivates a question, if I design a classical algorithm which is supposed to output this high energy state, what is the best ansatz for me to use? What is the best ansatz for approximation algorithms? It may be that by committing myself to the product state ansatz, I'm forcing myself to use a worse approximation algorithm than I could get with other ansatzes. Okay, so to zero in on all these problems, we're going to study a special case of the local Hamiltonian problem known as quantum max cut. So this is a special case of the two local Hamiltonian problem, which we saw earlier. And it's a special case in which the local matrix H is fixed. So no matter which qubits HUV we're looking at, we always have a single local matrix H, which is just given by 1/4 times the identity minus the poly XX minus the poly YY minus CZ. Now notice this Hamiltonian, since the local term is independent of the edge, this Hamiltonian actually only depends on the graph G. all I have to specify is which edges are there, and it specifies a Hamiltonian. And so I can always just write this Hamiltonian as HG. So I'm just going to rewrite it like that. And you remember our goal is then we're given the graph G, which describes this Hamiltonian, and we want to output the maximum energy state of Hg. Note that the maximum energy state of Hg is just equal to the minimum energy state of this thing right here. So the sum over all uv and the edges of x, x, y, y, and z, z. So that's just because we've negated the Hamiltonian and then we've thrown out the identity term, which doesn't change which state is the minimum energy state. And a Hamiltonian of this form is known as, it comes from the anti-ferromagnetic Heisenberg model. So this is like a well-studied class of Hamiltonians. They date back to a paper by Heisenberg in 1928, and there's like a lot of physics literature on these models. So this is kind of like a well-studied class of Hamiltonians. All right, so let me give a little bit of intuition for how this thing works. So let's say we have our state psi on n qubits. Maybe we're going to pick a constraint on from our Hamiltonian, maybe the uv term. And what does this Hamiltonian want these two qubits to look like? Okay, so this Hamiltonian, it has a term that contributes to the energy, which is this identity. And this identity term, it does really nothing. Like it doesn't, no matter what u and v are going to look like, we're always going to get the same amount of energy from this term. But this term, the xu and xv, the minus xu and xv, you should think of this as going to u and v, measuring them in the x basis. And when you do this, you're going to get, a plus or minus for each qubit. And what this term tells you is that you get a score of -1 if you get the same outcome. So when you measure them in the x basis, you either get 2 pluses or 2 minuses. But you get a +1 if you get different values. So if you measure them and you get a plus minus or a minus plus, then this term gives you a score of a +1. And you remember, we're trying to maximize the energy. We're trying to get the maximum score possible. And so what we want our state to do is have both of these look different when we measure in the x basis. We want to get a plus minus or a minus plus. So term 2 says that they should be different in the x basis. Term 3 says that they should be different in the y basis. And term 4 says that they should be different in the z basis. And so you can kind of think of this problem as like the classical, just like classical max cut, which asks that 2 qubits or 2 bits should look different. But now this is like classical max cut simultaneously in the x, y, and z bases. And so that's why this is called quantum max cut. Let me also say that this local term, another way of thinking of it is that it's just the projector onto the singlet state, if you're familiar with the singlet state. So it's a very simple family of Hamiltonians. Okay, now one special case of states that are really convenient to look at when you're looking at quantum max cut is product states. So again, a product state is of this form. It's a tensor product over all vertices in the graph of a single qubit state, psi u. So what this says is that if we have n qubits, then this product state is just going to give us like a single qubit state for each of these qubits. And product states, they possess no entanglement. So in some sense, they're kind of lame. But it turns out actually that many cases, product states can be close to the ground state of the Hamiltonian. So in particular, Brandau and Harrow in 2016, they showed that if the graph G is high degree, then the ground state is actually close to being product. Or in other words, there's a product state which is close to being, which has nearly optimal energy. Okay, so with product states, it's useful to look at their block sphere representation. So you remember with a block sphere, it just tells you that every single qubit state psi u can be associated with a real vector, cx, cy, cz. These are like the coefficients of the x, y, and z matrices in the block sphere representation. And since our qubit states are pure states, the block sphere tells us that this real vector is a unit vector. So the sum of the squares of these coefficients is equal to 1. So I'm just going to think of this, one way I'll think of this block sphere representation is just, since we have a product state, for every u, there's a block sphere representation. And so let me set f of u to be the function which maps u to its block sphere representation. Then f is just going to be a function that maps our vertices into three-dimensional unit vectors, i.e. the unit sphere in R3, which we'll write as S2. Okay, so pictorially our f then, it's just going to map each of our little yellow circles, each of our qubits, to a little three-dimensional unit vector. Okay, so that's our block sphere representation. F maps V into S2. And it turns out that given a product state defined with this F, it turns out that there's a really nice formula for the energy of this given a quantum max cut instance. So if we have a graph G and we look at the quantum max cut instant H of G, then the energy of our product state psi is just going to be given by this. It's sum over all edges in the graph of 1 minus the inner product of Fu and Fv over 4. What this roughly says is, we're trying to maximize this value. And so we want these inner products to be as negative as possible. And so that tells us that we want our neighboring kind of three-dimensional unit vectors to point in opposite directions, or as opposite as they can possibly point. This is a lot like the formula for classical max cut. So if you remember in classical max cut, you want to map each of the vertices to a plus or minus 1. And there you wanted to optimize, 1 minus f of u times f of v over 2. So it's exactly the same thing as in classical max cut, except classical max cut, you mapped your vertices into the zero sphere, so the one-dimensional unit sphere. Here we want to map it into the three-dimensional unit sphere. That's kind of cool. All right, so what do we now know about approximating quantum max cut? So the first thing that we know, let's see, this is due to Cubitt and Montanaro and Piddock-Montanaro. They showed that given an instance of the quantum max cut problem, estimating the maximum energy of the Hamiltonian Hg is QMA hard, so long as you want to estimate it up to really good error. So like inverse polynomial and N error. Okay, so this basically tells us that we can't hope to, exactly compute the maximum eigenvalue. And so people have instead started looking at approximation algorithms. So the first of these, this area was really kicked off by this work of Gribian and Perec in 2019, where they gave an approximation algorithm that achieved a 0.498 approximation, so almost a half approximation. The ansatz that they used was product states. So their algorithm, it took an HG and it would always output a product state of hopefully as good of value as possible. Follow-up work of Anshu, Gossett, and Morenz, they were able to improve this and get a 0.531 approximation. And they used a slightly more complicated ansatz. So what they gave was a state that their algorithm had always outputted a state which was a tensor product of 1 and 2 qubit entangled states. And then Perec and Thompson afterwards, they gave a 0.533 approximation algorithm, which also used the same ansatz as Anshu, Gossett, and Morenz. All right, and then in this last year, I guess, yeah, in 2022, we've had two works, one by Lee and one by King, that gave even better approximation algorithms. So they gave 0.562 approximations and 0.582, except with a minor caveat that this last one only currently works for triangle-free graphs. So only if your graph does not possess a triangle can you guarantee a 0.582 approximation. And the ansatz that these two works use, well, it's something even more complicated. All right, now one other thing, so why am I grouping these two like this? Well, the Gribian-Perec algorithm, it uses this level 1 SDP for the quantum max cut. So like the simplest SDP that you could write down for quantum max cut. Whereas these follow-up works do not use level 1 SDP, they kind of use more powerful versions of semi-definite programming. Okay, so finally I can get to our work. What was our motivation for solving or for studying this problem? Well, this Gribian-Perec work, like I said, they used a level 1 semi-definite program for quantum max cut. But these 4 other papers that came afterwards, they all managed to outperform it. Now, classically, it turns out the level 1 semi-definite program is actually optimal for for the max cut problem. So like the Gomez-Williamson algorithm just uses the level 1 semi-definite program. So, when I started working on this, I just figured like, well, probably Garibian and Prek didn't do a good job. Like maybe we could just do a better STP algorithm using the level 1 STP and improve on their algorithm. And like hopefully we can actually just show that this level 1 STP is optimal just like it is in the classical case. And I thought like, well, maybe what was the problem in the algorithm? Maybe it was because they're maybe it's because they're always outputting product states. And we kind of know actually that product states are just not the best ansatz in general. And so maybe you could improve on their algorithm by designing an algorithm that used a better and more expressive ansatz. So we spent actually a lot of time working on it and thought about it hard. And basically what I learned was, well, I was wrong in the beginning. And actually, well, what did we show? We showed that actually the Garibian-Prek algorithm is indeed the optimal algorithm, which uses the level 1 semi-definite program. So it's not like a mistake in the analysis. It's not like they gave a bad level 1 STP algorithm. Actually, they gave the best you possibly could do. So there's like one caveat here. Oh, I'll say the caveat later. So in other words, what this says is that any algorithm which uses a level 1 semi-definite program, not just a Garibian-Prek algorithm, has to have an approximation ratio that's at most 0.498. And for those of you in the know, I'll say this again later, but we show this via an inequality gap. So we design an inequality gap instance that has a gap of 0.498. We also show that it is NP hard. So that just rules out like using the level 1 STP. But we also give a theorem that rules out a larger class of algorithms. So we show that it's NP hard to achieve a 0.956 approximation for quantum X cut. So long as P is not equal to NP, then you can just never do better than 0.956. And again, this assumes it's unproven, but probably true unique games conjecture. Now, I will say that this bound, what we can show you can't achieve, 0.956, is far from what we know that you can achieve, 0.562. So this is a recent algorithm of Lee. And our result seems to be the limit of current techniques. So I think we really pushed like the limits of NP hardness techniques to get this 0.956. So I think we're going to need new ideas to bring down this hardness even further. But it should be possible. I don't know how to do it. And yeah, I think a great open question, can we improve either bound? Can we design a better approximation algorithm, or can we design a better NP hardness? Okay, what is this asterisk? Well, we assume a conjecture in Gaussian geometry. It's something called the vector-valued Borell's conjecture. We don't know how to prove it, and I'll explain what it is later. But let me just say it's like definitely true. So it just needs to be proved. Like someone in this audience maybe should prove it. But it's definitely true, I promise you. Okay, so that's our results. Let me give you the outline for the rest of the talk. My goal is just to explain the very first result that I told you about, that any algorithm for quantum X cut using the level 1 STP has to have an approximation ratio at most 0.498. And I'm going to do this with the following outline in 4 steps. First, I'm going to explain the Gomez-Williamson algorithm, so this classical max cut algorithm. Then I'm going to explain the Garibian-Prek algorithm for quantum max cut. Then I'm going to explain why the Gomez-Williamson algorithm is the optimal algorithm for the level 1 STP. This uses something called Borell's isoparametric inequality. And then finally, I'll explain actually our result, which is why Garibian-Prek is the optimal algorithm for the level 1 STP. And this assumes our unproven, but definitely true, vector-valued Borell's conjecture. Okay, so without further ado, let me begin with the Gomez-Williamson algorithm. All right, so the Gomez-Williamson algorithm, this is an algorithm to solve the max cut problem. So let me remind you what the max cut problem is. Your goal is to maximize the following expression: the sum over all uv in the edge of 1 minus fu times fv over 2, where f of u is always either plus or minus 1. Okay, so I'm going to draw this like pictorially. Let's say you have this number line, which goes in one-dimensional number line. We have 0, -1, and +1. And for max cut, what you're trying to do is, like, for every vertex, you want to assign it either a vector that points to the right, so to +1, or maybe for some of your vertices, you'll assign them to -1. So that's like a vector that points to the left. Now, you might ask, like, can we optimize over the best assignment of these plus or minus ones? But as we saw, it was NP hard. This is due to Karp's result from a long, long time ago. All right, but now let me change the problem slightly. And now, instead of asking you to just be on like the one-dimensional line, I'm gonna now have the vectors be in Rn, so n-dimensional real space. And if we do this, I'm just going to let you still only use one of these two vectors. So either you can point to the right and have +1 in your first coordinate and zeros everywhere else, or a -1 in your first coordinate and zeros everywhere else. And then in the expression, instead of having FU times FV, I'm just going to look at the dot product of FU and FV. Okay, nothing has changed. I've just embedded it into larger dimensions. But we still can't optimize over assignments that look like this. Why is this? Well, these just correspond to max cut assignments. I mean, nothing has really changed. But now what I'm going to do is I'm going to allow one final relaxation. Instead of allowing you only to use the vectors that point to the right or to the left, I'm going to allow you to assign f of u to be any unit vector in n-dimensional space. Any unit vector you want. Okay, so maybe like the best fu, actually you want to put it over here. And then the best fv, you want to put it over here. Then maybe fw, you want to put it over here, and so on. So it's like, every vector, you kind of want it pointing in as opposite of a direction as its neighbors as possible. That's what's going to give you the biggest max cut value. Turns out, though, that you can optimize over these vector assignments. I mean, it no longer really solves the original max cut problem. It's kind of like a higher dimensional version of it. But we can optimize over this efficiently. And the thing that finds the best vector assignment to all the vertices is known as a maximum cut semi-definite program, or SDP. So this is the level 1 SDP. It just finds these vectors. So let me write SDP sub max cut to be the value of the best vectors. And note that the value of the best vectors is always at least the value of the maximum cut in G. Why is that? Well, I can always, the maximum cut in G always corresponds to vectors that only point right and left. But maybe I can get an even better value by using these more general vectors. And this is what it means for the SDP to be a relaxation of maximum cut. It's always bigger than the max cut value. Okay, so Gomez-Williamson algorithm, step one, what it does is it runs the semi-definite program, and it uses it to compute these optimal SDP vectors. So maybe this is the vectors that the Gomez-Williamson algorithm starts with. And then step two, what it's going to do is a step called rounding. And what this is going to do is it's going to convert these vectors into a partition of the graph. Because remember, we're solving max cut. So ultimately, we need to output a partition. And this is called rounding. You convert the vectors into a partition. So these vectors are going to be in Sn-1, so n-dimensional unit vectors. And the rounding algorithm it's very nice. So what Gomez-Williamson is going to begin by doing is just picking a uniformly random vector z in n-dimensional space. So we're going to start by randomly picking something. This is going to be our z. And then what we're going to do is set our partition of the vertices as follows. For every vertex u in V, you're going to look at the inner product between z and f of u, and then you're going to take the sign of that, which is either going to be +1 or -1. So pictorially, what does that do? Let's draw this half space right here. The right is all the vectors that have positive inner product with z. The left is all the vectors that have negative inner product with z. Everything on the right, we assign a +1 to, and everything on the left, we assign a -1 to. So you can see this is kind of like a decent algorithm, right? Vectors that are very close to each other, they tend to get assigned on the same side as a cut, whereas vectors that are kind of pointing in opposite directions, they will tend to be put on different sides of the cut. And what Gomans and Williamson showed is that this achieves a 0.78 ... approximation ratio. Okay, so how do we analyze this to get this 0.878 approximation ratio? Well, what they actually showed was that the expected number of edges cut by the partition G is always at least 0.878 times the SDP value of F. So whatever value that this vector solution gets, this rounding thing will output a partition that gets at least 0.878 times that value. There should be an equal sign, but recall, the SDP value of F, that's going to be like an optimal SDP assignment. So it's always going to be at least the maximum cut in the graph G. So the expected number of edges cut by G is always going to be at least 0.878 times the maximum cut in the graph. Now, how do they show this inequality? Well, let's see. What do I want to say here? Let me just see. Yeah, so it turns out this inequality, it is tight. So we do know cases where you actually get 0.878 exactly. In particular, for every vertex u and v, let me write rho sub uv to be the inner product of the fu vector and the fv vector. Okay, so that's going to measure, how correlated these two vectors are. And it turns out that this Gomans-Williamson inequality is actually an equality if and only if the following is satisfied. For every edge in the graph, this rho uv, so the inner product between these two vectors, is exactly equal to minus 0.69. So if all the vectors that are connected by edges have this one kind of bad dot product, or maybe let's call it the bad angle, if everything in our SDP has a bad angle, then we will indeed lose this 0.878 factor. But if they don't have this bad angle, then we'll actually do better than the 0.878 factor. All right, so that's Gomans-Williamson. Now let me tell you the Grivian-Perec algorithm for quantum X-cut. So yeah, let's go back to the quantum X-cut problem. Our goal now is to tell you about their 0.498 approximation algorithm. And let me recall, it's based on the level 1's SDP, and it always outputs a product state. Okay, and what's a product state? Well, it's none other than a block sphere assignment. So it maps the vertices V into the three-dimensional unit sphere. Okay, so what is semi-definite programming? Well, or how do we design the semi-definite program for quantum X-cut? Well, I'm not going to tell you, but let me just give you like a high-level intuition. So it turns out for every optimization problem, there is like a generic level 1 SDP that you can write down. Just like in the classical max-cut problem, in the quantum max-cut, this SDP will give you an upper bound to the true optimum. You can efficiently solve it in polynomial time. And it's probably going to involve some vectors, okay? Now, for quantum X-cut, it's a bit complicated to say exactly how we define this semi-definite program. But it turns out that after you write it down, you can do some magic and simplify it. And the simplified form is like, oh, it's really nice. So it turns out, given a graph G and its corresponding Hamiltonian H sub G, the corresponding SDP is exactly this right here. So the SDP for quantum X-cut of this graph, it's just the maximum over, well, you sum over all edges u and v in E of the quantity 1 minus 3 times the inner product of fu and fv over 4, subject to f mapping every vertex into the n-dimensional unit sphere. All right, this is very, very, very similar to the max-cut SDP. So the max-cut SDP, to remind you, it was the exact same thing, except it was 1 minus, we didn't have a 3, so just 1 minus fu inner product fv divided by 2. So it's the exact same thing up to like a small linear transformation. And what that means, for example, is that the optimizing function f is actually the same optimizing function in both cases. So basically, they're the same SDP up to a small linear transformation in the value. I want to say this, to me, was very surprising. I mean, there's no reason this had to be true. But yeah, you do it, it's magical, and it turns out to be true. Okay, and just like I said earlier, this STP will give an upper bound to the true optimum. So Q max cut of G is always less than or equal to the STP value of G. And once we have this, what we need to do is round it into a block sphere assignment. So a function G that maps the vertices into the three-dimensional unit sphere. The question is, well, how do you do this? I mean, how is this possible? And this was answered by the Gribbian-Freck algorithm. Okay, so step one, what do? They compute these optimal STP vectors. Maybe they look like this. Step two, what they're going to do is round them into a block sphere assignment. And the way they're going to do it is as follows. They're going to pick a random three-dimensional projection matrix, pi. So this pi, it's going to be 3 by n, and it's going to map n-dimensional vectors into three-dimensional vectors. So pictorially, we can specify pi like this. It's going to have 3 rows. Let me call the first row x, the second row y, and the third row z. And x, y, and z, we're going to pick them to be just 3 random vectors, which are orthonormal to each other. So they're unit vectors and they're orthogonal to each other. And then for every vertex in the graph, what we're going to do is we're going to set the block sphere assignment, G of u, to just be what we get when we take our vector, fu, and we project it down to 3 dimensions using pi. Except, for a block sphere assignment, we always need to output a unit vector. And this thing may not be a unit vector, so the last thing we have to do is normalize it. Okay, so pictorially, what do? Well, if this is our pi, our randomly selected three-dimensional subspace, then the first thing we do for a vector is we project it down to pi. So we put fu down there, and then we have to renormalize it. Similarly, and that thing is going to be called GU. Similarly, for FV, we map it down into pi, and then we have to renormalize it as well, and that's going to be called G of V. Okay, so we project, and then we normalize, and that gives our block sphere assignment. And just like in the Gomans-Williamson case, this will tend to map, similar vectors in n dimensions down to similar vectors in 3 dimensions, which is basically what you want. And what they showed is that this algorithm achieves a 0.498 approximation ratio. Okay, how do we analyze this algorithm? Well, it has a very similar analysis as a Gomans-Williamson algorithm. So what Gribbian-Freck show is that in expectation, the energy, the value of this of G that they output is at least 0.498 times the STP value of F. So just like in the Gomans-Williamson case, once you have this immediately gives you that you output at least 0.498 times the optimum value. And this also has like a similar tightness condition, like in Gomans-Williamson. So again, if we set rho uv to be this angle between the vectors fu and fv, then it turns out that their inequality is also an equality if and only if, for every edge in your graph, this angle, rho uv, is minus 0.97. So this rho star of minus 0.97, this is the bad angle for the Gribbian-Freck algorithm. If there's some edges not at this bad angle, then you'll actually do better than 0.498. But if they're all at this bad angle, then you get exactly 0.498 times the STP value. Okay, so that's the Gribbian-Freck algorithm. And now let me finish the final 2 parts. First, why is Gomans-Williamson optimal for the level 1 STP? Okay, so in the Gomans-Williamson algorithm, let me recall how we analyzed it. We wanted to show that the expected number of edges cut by the G that you output is at least alpha times the maximum cut in the graph G, where alpha was this number 0.878 ... But what we actually showed was something stronger, which is that the expected number of edges cut was at least alpha times the STP value. And this is a stronger statement because the STP value is always bigger than the max cut value. But this is the standard way people analyze STPs. This is called the standard analysis, which is that you compare the value of G not to the max cut value, but to the STP value. Okay, let me note something with this. Since we showed this, if you analyze it by the standard analysis, you do know that the expected number of edges cut by your cut G is always less than or equal to the maximum cut of the graph, because G is a cut, so it can never do better than the maximum cut. And so because we showed this statement, whatever alpha we pick, it has to be, like if you divide both sides by the STP value of the graph, alpha can never be less than or equal, or sorry, it always has to be less than or equal to the max cut divided by the STP value. It can never be bigger than this. So one thing you can do then, if you want to upper bound the best alpha that you can ever prove with this analysis, is you can just look at this ratio and take the minimum over all graphs G. And this is known as the integrality gap of the STP. This is when you minimize it, it tells you what is the largest amount by which the STP overestimates the maximum cut. And if you compute this integrality gap, it's going to tell you a limitation on any algorithm that you analyze via this standard analysis, where you compare G to the STP value, not to the original max cut. Okay, so what do we know about max cut? Well, it turns out that Feige and Chapman showed that the level 1 STP for max cut actually has an integrality gap of 0.878, which exactly matches the algorithm of Gomez-Williamson, and it shows that their analysis was tight. Yeah, so any algorithm which rounds the level 1 STP, this proves has an approximation ratio of at most 0.878, at least if you analyze the algorithm according to this standard analysis. Raghavendra later showed that actually for any constraint satisfaction problem, the optimal polynomial time approximation ratio that you can achieve is exactly equal to the integrality gap of the level 1 STP. Or sorry, this basic STP, and in the max cut case, this is equal to the level 1 STP. Again, this result assumes a unique games conjecture, but that's probably true. So what this tells us actually is that we can't beat the standard analysis. I mean, the standard analysis is like the right way to analyze STPs. Okay, so now what we have to do is, I should tell you, what is this integrality gap or max cut that Feige and Chapman constructed? It's something called the Gaussian graph. So the Gaussian graph, it's a graph, it has vertex set Rn. So actually every n-dimensional point is a vertex in this graph. And a random edge in this graph is going to be distributed as follows. So I'm not going to tell you the edge set, because that's going to be harder to specify, but let me at least tell you how to sample a random edge from this graph. So a random edge is distributed as follows. You just pick two row correlated Gaussians, U and V, and output the edge between U and V. And what they do is they pick rho to be this bad angle minus 0.69. Okay, so what is a row correlated Gaussian? Well, pictorially, it's like you pick a uniformly random Gaussian vector somewhere else. And then you pick another vector, which is kind of, well, in this case, negatively correlated. So we have a negative correlation of minus 0.69. If it was minus 0.1, then it would be like exactly the opposite vector. But since this is only like somewhat negatively correlated, then we're going to get something that's kind of pointing in the opposite direction. And that will give us our V. So it turns out that the optimal STP, so this is our graph. And now the question is, like, what is the optimal value? And also, what is the optimal STP solution? So the optimal STP solution for this graph, it turns out, for every vertex, the STP will just map it in like almost the obvious way. So what the STP is going to do is take every vector U. It has to output a unit vector. You remember the STP always outputs unit vectors. So it's just going to take U and normalize it. And it turns out that if you do this, then for most edges in the graph, U and V, because U and V are row correlated, then the inner product of these two vectors, FU and FV, is going to be roughly equal to this rho, which is this bad angle. And this tells us, actually, because in this graph, all of the vectors in the STP solution are at this bad angle, this tells us that the value of the Goemans-Williamson solution is always going to be equal to 0.878 times the SDP value of f. Okay, so whenever we round using Goemans-Williamson, we will indeed lose a factor of 0.878. Okay, but what we really want to show is that the optimal value is equal to 0.878 times the SDP value. If we get that, then we have that optimal divided by SDP is equal to 0.878, and that gives us our inequality gap. So what we need to do is show that whatever Goemans-Williamson gets is actually equal to the optimal value. Okay, so how do we show that? Well, let's remember, how does Goemans-Williamson work? What it's going to do is it's going to pick a random vector. Then it's going to look, that's R. It's going to look at all the vectors on one side of this half space. It's going to assign them all +1. And then all of the vectors on this side, it's going to assign them all -1. So the value of our solution is just going to be this. It's going to be the expectation of, you pick U and V row correlated, of 1 minus G of U times G of V over 2. And G is going to be this thing that we just saw. So G of U, it's just going to take U and a product R and take the sign of that. G of V, it's going to take V and a product R and compute the sign of that. Now this thing is actually rotationally symmetric. It doesn't matter which R we pick. So we might as well just assume that we always pick the R, which is like the first standard basis vector. So 1 followed by all zeros without loss of generality. If we do that, the inner product of U and R is just going to be U1, and the inner product of V and R is just going to be V1. Okay, so what we want is that this partition is the optimal partition. We want this to be the optimal value of the max cut instance. And we want it to be at least this expectation. So the expectation over UV of 1 minus HU times HV over 2 for all partitions of the vertices H. And this is what Borell's theorem, so Borell's isoparametric inequality, tells us, is that this quantity, the expectation over all U and V of HU times HV, is actually minimized when HU is just the sign of U1. This is like the negative row version of Borell's theorem. There's also a positive row version of Borell's theorem. This was first proven by Borell in 1985. It's a basic result in Gaussian geometry, and there are like a million different proofs of it at this point, so it's very fundamental. But this is a statement that you use to prove that the Gaussian graph is an inequality gap. All right, I know I'm like eating into my questions. I apologize for that, but yeah, now I'm at the final part of the talk. So let me finally explain, why is the Gribien-Perec algorithm optimal for the level 1 SDP, which is now our result. Okay, so we have to come up with an inequality gap for quantum max cut. What we showed is that the level at 1 SDP for quantum max cut has an inequality gap of 0.498. And actually, we're going to use the exact same graph as in the classical max cut case, the row correlated Gaussian graph, except we're going to use a different row, a different bad angle, which is a bad angle for the Gribien-Perec algorithm of minus 0.97. And because we use this bad angle, this immediately tells us that the value of the Gribien-Perec solution is going to be exactly equal to the 0.498 times the SDP value of f. So Gribien-Perec will definitely lose a factor of 0.498. And so therefore, we have to show that whatever the Gribien-Perec solution outputs is actually equal to the value of the optimal cut. Okay, so how do we show this? Well, remember, Gribien-Perec, it's going to pick a random 3-dimensional projector pi. And it's going to set, it's going to round the vector u. It's going to project it down onto pi and then normalize it for every vector u and r to the n. So the value of the solution is just going to be this. It's going to be expectation over uv 1 minus the inner product of gu and gv over 4. Again, this is rotationally symmetric. So we might as well assume that pi projects u onto the first 3 coordinates. And in this case, g of u is just going to be, it's going to project you onto u1, u2, and u3, and then normalize it. So what we would like is that for this G, we want it to be the optimal quantum state. We want this product state assignment that Gradient-Perec outputs to be the optimal quantum state for this graph. But you remember, this is a product state, so we're defining it in the block sphere representation, but this is just a product state. But we need to show it's not optimal just among product states, but among all quantum states, even ones that are entangled. But fortunately, our graph G is high degree. It's not just high degree, it's infinite degree. And so we saw earlier that if your graph is high degree, that immediately tells you that there is a product state, which is an optimal ground state. So this is due to Brandau and Harrow. And so this means that we don't actually have to compare against all quantum states. We only have to compare against other product states. So this motivates this conjecture that we made, the vector-valued Borell's conjecture, which states that for all k greater than or equal to 1, the quantity expectation over uv of the inner product of hu and hv is minimized whenever h just takes outputs the first coordinates of k and normalizes them. And this is basically equivalent to the statement that Gradient-Perec outputs the optimal solution on the Gaussian graph. Again, this is a negative rho version of the statement. There's an analogous version when rho is positive. We thought we had actually proven this. So, we wrote up a proof, we put it in the paper, we put the paper on the archive. But Steve Heilman actually found a bug in our proof. He actually emailed this to us the day after Christmas. So it's a very sad Christmas when I got that email. But yeah, it was very good on Steve for finding it. What we can show is the following. First, we can show that any h that that any optimal h is essentially k-dimensional in the sense that really it only uses like k kind of coordinates. And we show this using the calculus of variations. And then, so that kind of reduces you to the case when the ambient dimension n is equal to k. And then we can actually prove this statement in the case when the ambient dimension n is actually equal to k. And we show this using Fourier analysis. You might say, well, 1 plus 2 together, that definitely looks like a proof, right? Well, yeah, that's what we thought too. But it turns out that our proof for 1 actually only works in the case when rho is positive. And 2 only works in the case when rho is negative. So it's like we have these two puzzle pieces and they almost fit. If we could prove both of them for the positive rho case, it turns out we'd be done. If we could prove both of them for the negative rho case, we'd be done. But we don't know how to prove, we have this weird mismatch for the rhos that we know how to prove. But earlier this year, Steve Heilman got us like another Christmas present, this one much nicer, where he actually showed that the vector value Borell's theorem, or Borell's conjecture, is true. Okay, that's great, we're all done. Except there's a small catch. He's only able to get it for the parameter regime when rho is less than or equal to 0.1, an absolute value. And we need rho to be minus 0.97, so very close to -1. But we're close. I mean, I think, hopefully, give Steve another year. Maybe he'll solve it. Hopefully, someone in the audience will solve it. I think it's definitely true. It just the technology is almost there, just not quite there yet. All right, let me conclude just with some open problems. Sorry, I'm running late. Okay, open problems. Number 1, you should just prove the vector-valued Borell's conjecture. It's a great conjecture. Someone should prove it. Number 2, we should improve the unique games hardness past this 0.956. I mean, I think it'd be very cool to even get 0.955. I think that would require brand new techniques. So I'd be very excited by that. It'd be great to improve the best approximation ratio past 0.562. I definitely know it's possible. I mean, it has to be. I just don't know how to do it. Okay, this Perec-Thompson algorithm I mentioned earlier, as well as basically all the other algorithms aside from Gradient-Perec, they use this level 2 sum of squares algorithm. It's a more powerful semi-definite program than the level 1 SDP. And a great question is, maybe we don't know what the best algorithm is out there, but can we at least understand these small semi-definite programs? The last thing I really want is something called an algorithmic gap. So I gave an integrality gap for the Gradient-Perec algorithm, which shows when the SDP does poorly. But we don't actually know of a graph G where the quantum max cut of the graph is some value V, but Garibian-Perec produces a state with energy 0.498 times V. So we don't actually know of a concrete graph where Garibian-Perec actually gets 0.498 times the optimal value. You remember, we just proved in Gaussian graph that Garibian-Perec actually gets the optimal answer there. It could then be that the standard analysis is not tight. It could be that actually, even though we have an integrality gap of 0.498, maybe the standard analysis is not tight, and maybe Garibian-Perec actually gets a 0.5. That to me would be like shocking and amazing. Let me just say one more thing. Okay, one more open problem. I'm really sorry for taking advantage of your time, but I really like this one. What if instead of defining the quantum max cut Hamiltonian, we define the EPR Hamiltonian, Hg, where instead of every local term projecting to the singlet state, we projected to the EPR state. This problem turns out to be equivalent to quantum max cut on bipartite graphs. So if you only care about bipartite graphs, you might as well just study this problem. We know of an algorithm with an approximation ratio of 1/√2 due to King, Wright and King. This Hamiltonian, it's a stochastic Hamiltonian, so it's not a general QMA complete Hamiltonian. It's in stochastic MA, but it's also not known to be stochastic MA complete. It's also not known to be in P either. So I think this is a great open question. What is the complexity of this Hamiltonian? Is it in P? Is it stochastic MA complete? And if it is, what is the best approximation we can get for it? All right, thanks.
Okay, thanks, John, for a great talk. So any quick questions for John?